we've built up a pretty solid mental model of transformers, how they use self-attention to process sequences, and their power in generating text, thanks to hashtag TCM183000.
Exactly. But for all their power, there's a nagging problem with text generation. It's inherently slow. Each new token depends on the one before it, so it's a serial process.
You mean like waiting for each word to pop up one by one in a chatbot? It still feels sequential, even on a fast GPU.
Precisely. And that sequential nature is a bottleneck. Today, we're going to explore speculative decoding, an idea that dramatically speeds up this process without changing the output.
Wait, if it's inherently sequential, how can we make it faster without changing the output? That sounds counterintuitive.
It's a clever solution to a fundamental problem. This paper, Fast Inference from Transformers via Speculative Decoding, clearly identifies the core problem.
So what's the trick? Are we just running the model faster somehow?
Not exactly. The paper states the problem. Decoding K tokens takes K serial runs of the model. This is the bottleneck we're directly addressing. The authors state the problem clearly. Decoding K tokens takes K serial runs of the model. This serial dependency is why inference from large models is slow.
Okay, K serial runs means K separate computations, one after another. That explains why generating longer sequences is slow.
And this bottleneck is significant. For example, the paper showed a 2x to 3x acceleration compared to the standard T5x implementation with identical outputs. That's a massive speedup for something computationally intensive.
Right. And their solution is an algorithm to sample from autoregressive models faster without any changes to the outputs by computing several tokens in parallel. Computing several tokens in parallel? How does that not change the final output?
That's the key. Imagine you have a really smart but slow friend and a slightly less smart but super fast friend. They work together.
Okay, like a brilliant professor and a very quick, efficient TA.
Exactly. The slow professor is the target model, our big LLM. The fast TA is a draft mechanism. The TA proposes answers quickly, and the professor just checks them.
So the TA is guessing and the professor is verifying. That's the core idea.
Exactly. Now, where this analogy differs slightly is that, unlike a human TA, our draft model isn't learning from the professor's corrections in real time, but rather making its best guess based on its own training. And the professor doesn't just correct, they can also choose to rewrite entirely. This paper highlights an important observation. Hard language modeling tasks often include easier subtasks that can be approximated well by more efficient models.
So the fast TA can handle the easier subtasks perfectly fine, without needing the professor's full brain power.
Yes, and the critical insight is that using speculative execution and a novel sampling method, we can make exact decoding from the large models faster.
Exact decoding. That's really important. It guarantees the same final answer as the slow method.
This speculative execution idea isn't entirely new. We see it in computer architecture, where CPUs predict future operations to keep their pipelines full.
So it's like the CPU guessing what instruction will come next to avoid waiting and keep busy?
Precisely. Here, we're guessing future tokens with a lightweight model, then feeding those guesses to our big transformer to quickly check.
And this avoids the K-serial runs bottleneck of traditional autoregressive decoding?
By doing this, we can achieve generating several tokens concurrently and without changing the distribution. This without changing the distribution means identical outputs.
This identical output guarantee comes from a clever trick called rejection sampling. Essentially, the target model doesn't just check if the draft token is plausible, it checks if the draft token would have been the exact token it would have produced itself with the same probability distribution. If it wouldn't, it's discarded.
So the big model still decides the final probabilities for each token, even if a smaller model made the initial guesses?
Yes, the main model always has the final say and generates the exact same sequence as if it ran serially. The draft model just makes the process efficient.
The goal is clear. Accelerate inference from large autoregressive models like transformers without any compromise on output quality.
It sounds like we're using a smaller, faster model to do the grunt work, then letting the big model do a quick check on a batch of proposed tokens.
That's the high-level picture. Now let's dive into the NVIDIA blog to build a more concrete intuition for how this draft and verify mechanism actually works.
I'm ready for the intuition. How does this TA and professor idea really play out technically?
The NVIDIA blog uses a useful analogy to explain the core idea. Speculative decoding works much like a chief scientist in a laboratory, relying on a less experienced but efficient assistant to handle routine experiments.
So the chief scientist is our big, powerful LLM, and the assistant is the draft mechanism that helps it along.
Exactly. The assistant rapidly works through the checklist, proposing tokens, while the scientist focuses on validation and progress, checking multiple proposals at once.
And the scientist only steps in to correct or take charge whenever necessary, ensuring accuracy.
Yes, much like a scientist trusts their assistant's routine work. But a key difference here is that if the assistant model makes a mistake, the scientist model has a very precise mathematical way to detect it and either accept a partial draft or discard it entirely, ensuring the final output is exactly what the scientist would have written, which isn't always the case with human collaboration.
The article states, by predicting and verifying multiple tokens simultaneously, this technique shortens the path to results and makes AI inference faster and more responsive.
So it's about breaking that sequential bottleneck we talked about earlier, allowing the process to become parallel where it can.
Yes, instead of one token at a time, we're processing a batch. The benefit is reducing latency while preserving output quality.
Preserving output quality is crucial. No one wants a faster but dumber chatbot or a changed answer.
This approach is a direct answer to the fundamental bottleneck of autoregressive generation. Each token requires a full forward pass, reloading weights, and synchronizing memory at every step.
We built up the transformer architecture in hashtag TCM183000, so I understand the forward pass. Doing that repeatedly for every token sounds incredibly inefficient.
It is. It underutilizes hardware and limits system efficiency. Speculative decoding directly tackles this by allowing the system generate multiple tokens at once. So what is speculative decoding? It's an inference optimization technique that pairs a target model with a lightweight draft mechanism that quickly proposes several next tokens.
A target model and a lightweight draft mechanism. This sounds exactly like our professor and TA analogy.
Precisely. The target model is our large, slow LLM. The draft mechanism is something fast that generates guesses. It predicts the likely next tokens.
And then the target model verifies those proposals in a single forward pass. That's the parallelism. So the draft model is essentially taking a shortcut, giving the target model a head start on what to check.
You can think of it that way. The lightweight assistant model proposes multiple possible continuations, and the larger model verifies them in batches.
It's like getting several pages of a draft report from the assistant, and the scientist just has to read through and mark corrections instead of writing it all.
Right, and unlike a human report where the scientist might accept a slightly different wording, here the verification is absolutely strict. The target model will only accept tokens if they are exactly what it would have generated itself. This rigorous token-by-token validation ensures that the final output is identical to what the target model would have produced, guaranteeing that the speedups come with no loss in accuracy.
That's a good mental picture.
The ultimate benefit is reducing the number of sequential steps, alleviating memory bandwidth bottlenecks.
What if the assistant is really bad at guessing? Does that make the process slower than just using the professor directly?
That's a key point. The speedup is maximized when the draft mechanism is good at its job. If it proposes mostly incorrect tokens, the target model spends more time rejecting.
So, a poor draft model could actually hinder performance rather than help because of all the rejections.
Exactly. The ideal scenario is when the draft proposals are frequently correct, minimizing the need for the target model to regenerate.
The draft target approach is the classic implementation of speculative decoding, operating as a two-model system.
Two models. So we need to have a smaller model specifically to do the drafting, in addition to the main LLM?
Typically, yes. It's often a much smaller, faster draft model, which is often a distilled or simplified version of the target.
Like a mini-me version of the big LLM trained specifically to make quick, decent guesses?
This partnership, where the draft model quickly producing 4 draft tokens for the target model, which verifies and keeps 2 while also generating 1 additional token itself, is the core dance.
Okay, so the smaller model drafts, the bigger model checks, and then fills in any gaps. I'm starting to see the workflow clearly.
Now, let's zoom in on the mechanics that make it effective. Specifically, how that verification and acceptance process actually works to ensure identical output.
I'm curious to see how it decides what to keep and what to throw away, and how that guarantees the same result.